we're going to move on to a specific type of continuous variable. If you remember, our quantitative variables or numerical variables had two types. Discrete were described by counting variables or distinct points on the number line, and we had a specific type of discrete variable called the binomial distribution. Now we're moving on to continuous variables, so anywhere on a number line we can have decimals and so on. And the specific type we're going to talk about is the normal distribution. You already have some familiarity with this. Remember from earlier, the bell-shaped symmetric distribution we had, and we were able to use the empirical rule to describe probabilities associated with that distribution. Now, a lot of real-world data follows this bell curve shape, and also we have some important theoretical results later where the shape will be very important. So we're going to spend some time on this bell-shaped distribution or normal distribution. And just like binomial, we have some shorthand notation. We're going to use x to represent the variable we're talking about, so any continuous variable that follows a bell curve, height, weight, concentration, time, anything. If it follows a bell curve, we're going to say that variable can be modeled by, it's how we read our tilde. We're going to use capital N to represent normal. And again, by normal, we're saying it has the bell curve shape to it. So never plug in a number for this. Use capital N to mean bell curve. And then we're going to put in a couple pieces of information. And the first one is mu, the mean. And the second piece of information is going to be sigma, the standard deviation of the population. So our variable can be modeled by this bell curve with a center of mu and a spread described by sigma. So let's review a little bit and go through an example here. So in this example, they tell us the average age of Major League Soccer teams adjusted for playing time was 27.9 years with a standard deviation of 1 year. And they also tell us the important information that the distribution is unimodal and symmetric. So we're going to write down that information in our shorthand notation here to be handy later. So x, our variable for ages of Major League Soccer teams, can be modeled by capital N, because they tell us it's unimodal and symmetric or bell curve. Then we need to say where it's centered. So they tell us the mean or the center is 27.9. That's our mu. And then the spread they tell us, or our standard deviation, is 1. That's our sigma. So there's that paragraph summed up in our convenient notation. The next several questions kind of ask about areas under this bell curve, which we're familiar with. So to aid in answering those, at the bottom of the page, let's first draw that empirical rule picture. So I'll draw my bell curve, and we'll see what we can remember from earlier in the semester. So they tell us this mean or balance point here is 27.9 years. And if I go one standard deviation on either side, the standard deviation is 1. So that makes it easy. We're just going to add 1 and subtract 1. Then we should have about 34% of our observations here, or 68 within that first interval. If we go one more standard deviation in either direction, so again our standard deviation happens to be 1, making this easier to count, we've got another 13.5% or 95% altogether. And then our last bit, if we go one more standard deviation in either direction, we should have nearly all of our data, so about 100%, which gave us 2.5 in either piece. So we're familiar with this setting. I'm going to label this row X for a moment. There's our variable representing age, and here's our empirical rule breakdown for that. And we can use that to answer questions fairly easily. So for example, the first one, what percent have an average age between 25.9 and 29.9? So here's 25.9 and 29.9. So that's 2 standard deviations on either side of the mean. If you add all those up, or if you just remember, that's 95%. I'm going to rewrite this in probability notation since we have been working on that. So 25.9 and 29.9. So in this notation, it's saying find the probability that x, this variable representing age, is between these two values. And we know from the empirical rule that that's approximately 95% or 0.95. Let's jot down the next one. The probability of an average age greater than 28.9. So x is greater than 28.9. And since we've drawn the picture, pretty easy to see, above 28.9 is 16% of our observations, so 0.16. And then the last one here, what percent of teams have an average age less than 27? If we take a look, this one's a little bit trickier. 27 is nowhere on the scale that we've drawn exactly 1, 2, or 3 standard deviations from the mean. 27 is like right here. It's not quite 1 standard deviation below the mean. So we can't really answer this question with any accuracy. We know it's going to be 2.5 plus 13.5, so 16 plus a little bit more, this other sliver of area, but we can't quite answer that accurately. So I'm just going to put, for the moment, don't know. We know it should be a little more than 16% based on our picture, but we can't say much more than that. So this points out that this empirical rule certainly has limitations. Why would I be interested in 28.9 years of age? That seems kind of random. 28 might be more interesting, or 27.5, or 29. A lot of values that aren't even on here. So we need to make information about this bell curve more generalizable. And that's what we're going to do in this section. So the first thing we're going to be doing is converting whatever scenario we're dealing with to this common unitless scale. What have we talked about before that has a common unitless scale? Sure, z-scores have a common unitless scale. So if you remember, the mean here right in the middle has a z-score of 0. This guy would have a z-score of 1 because I've gone 1 standard deviation above the mean. This one would have a z-score of -1 because I've gone 1 standard deviation below the mean. Z-score of 2 if we worked it out because I've gone 2 above, and 3. And then same thing down here, -2 and -3. And then also just as a reminder how we found those z-scores, I might just say recall z is equal to our observation minus the mean over the standard deviation. So that's how we calculated that kind of common unitless value here. And if you want to double check, take this observation, subtract 27.9, divide by 1, you'll get -1. All right, so our goal is to be able to find area under the curve, not just for these boring 1, 2, or 3 standard deviations away, but for any number in here. Area under the curve, if you've had calculus, you're probably going to be integrating, except there's a teeny tiny problem. The mathematical function that defines this curve cannot be integrated in a closed form. Therefore, our calculators are going to estimate this area for us. And to do that, we're going to first convert everything to this common unitless z-score scale So for example, when I convert that 27, it should be a z-score that's somewhere between -1 and 0. I'm going to convert it to that common z-score scale and then ask my calculator to estimate the area of interest. So for the next video, make sure you grab your calculators and I'll show you how to find these areas under our curve.